In this video, I'll be working through the solutions to the second midterm of Physics 455, specifically question 1. Question 1 reads that we have a very long rod with a charge density lambda, as we can see here in the diagram, with a width of w and it's a distance d above a large conducting plane. So we can see right away that the rod is in and out of the page. So we can just kind of see it from the end. So it looks kind of like a circle, as if you were looking at a cylinder from the end. It has a width of w, a charge density of positive lambda, and it's a distance d above a large conducting plane. So if we assume that this conducting plane is large enough that it's kind of infinite in all directions, and we assume that the rod is moving in and out of the plane, and we also assume that it's essentially infinite in length, then we can essentially treat this as a method of images problem. We can see that we kind of have a charge above a plane, and it's going to have some sort of effect on that conducting plane so that the charge moves around, and we have some sort of image charge below. So part A of this question asks to draw the configuration of the image charge or charges and explain what that configuration would be. So we can start by looking here that we have a positive charge density lambda above the plane, and therefore we can kind of think, based off the method of images, that we might have some sort of charge reflected below. So we have something here, similar distance below, just like if we had a point charge above and point charge below, we have some sort of reflection across the conducting plane. We can say that it has the same width, and we can say that it's going to be a rod as well, a rod that's in and out of the plane, infinite in length, of the same width w, but in this case we're going to have a negative charge density lambda, and that's because, again, when we have that image charge, it has to be such that it's like a mirror image. So if we have a positive charge here, it has to be negative down below when we take that mirror image. So this is what part A is we have this reflection, this negative image charge of a negative charge density lambda with the width of w. Again, it's a rod infinite in the whatever axis this is, in and out of the board in this case, a distance d below the conducting plane. Part B asks for us to explain why this is the charge configuration and what physical conditions must be met so that this is true. So my argument always for this kind of problem has to do with the electric field, and it also has to do with how the potential is going to be across these two planes. In this case, when we have our rod here, and we have our image rod here, we're essentially going to have electric field lines coming down off of the rod, like so, and from the negative side we'd have it going like this to kind of meet up. And at that conducting plane, at that place exactly between the two rods, is essentially going to be an equipotential surface. Now this, if we have a positive lambda here and a negative lambda here, looks a lot like a dipole. And of course, at the place exactly between the two charges of a dipole, we have an equipotential surface, essentially splitting that dipole in half. And that's what we have here. So the reason this has to be a negative charge and has to be the exact distance below the plane, so we have a d here and a negative lambda here, is because we essentially have this dipole set up, and in order to get this equipotential surface to exactly cut this dipole in half, this is the charge configuration that we have to have. And this kind of also answers part C right away when we say draw the electric field for this configuration of the charge and the conductor, in that when we have this this positive charge density lambda on the infinite rod above the conducting plane, the electric field is going to come off like a dipole and be exactly perpendicular to the conducting plane at all points, like so. So we're going to have the electric field kind of coming off, and if we had more, essentially it would curl around, and again, always be perpendicular at that conducting plane. And we can maybe see it a little bit better in this diagram, since the image charge is not supposed to actually have an electric field below the conducting plane, because of course there is actually no charge down here. So these field lines are only to kind of conceptually see that it's a dipole, but of course we're only going to have the electric field in the region above the conducting plane, because that's where the charge is. We don't really know what's going on below that conducting plane, and the conditions are that this electric field must be perpendicular at all places on that conducting plane. So that was parts A through C of question 1, and I kind of went through it quickly because we've seen quite a few videos on the method of images and what happens when you have simply a conducting plane and a charge above and below. In this case it was different because we had a rod of charge, but when you're looking at it from the end, it essentially looks like one single circular charge anyway, so you can kind of think of all the same processes that we had before in the other method of images problems. In this case, in part D, we have a little bit of a different setup, and you can see from the diagram that I've already drawn that the conducting plane in this case and the infinite rod, you can see that there's definitely some sort of length to it now, and we can't just look at it as if it was a single point charge looking at it from the end above the conducting plane. Question 1 part D reads that we have a line of charge that runs along the x-axis, so you can see I've drawn the x-axis here, y-axis and z-axis, and we want to find the potential V at some point 0, y, and x above the plane. So again, we have our rod of charge that has a positive charge density lambda, a width of w, and it's a distance d above the plane. And right away I'm going to draw in the image charge because distance d below, because we know that from parts A through C, this is kind of the setup that we're going to have right away. And we're also going to have a width of w. So we know that from parts A through C, this is the eventual configuration that we're going to have, where we're going to treat this setup as if it had an image charge of negative charge density lambda below the conducting plane. So I'm going to draw that in right away just so we can see that from parts A through C. That's why we thought about what was happening above and below the plane in order to solve this problem. So in this case, you want to know what is the potential from a line of charge, but I know that I definitely did not remember what this was at first. So we'll go ahead and solve that first, just to show that you can in fact determine what the potential from a single line of charge is just by knowing Gauss's law. So we'll recall that Gauss's law says that the closed integral of E dotted with dA is equal to Q enclosed over epsilon naught. Now, I'm going to skip a few steps because this is not a Gauss's law problem, but you can essentially watch the other videos on those kind of problems to see where I'm going with this. But essentially we'll have the electric field multiplied by 2 pi s times some length L, where this is our Gaussian surface with an area 2 pi SL, and the charge that's enclosed by that Gaussian surface, if we put that around the line of charge, will be lambda times L over epsilon naught. And this gives us an electric field of lambda over 2 pi s epsilon naught in the s hat direction. So that's the electric field from a line of charge. Now the potential is given as the negative integral from the origin to our point of interest of E dotted with dl, which in this case is going to be the integral from the origin to the s of lambda over 2 pi s epsilon naught s hat dotted with ds s hat, which if we solve this integral, we can see that the s hat and the s hat, the dot product will just give us 1, and we integrate from some position to a position s over 1 over s ds, which is going to be a logarithm. So this ends up giving us lambda over 2 pi epsilon naught logarithm of s. And you can check that at home, that this is in fact the potential of a line of charge, given that we know the electric field. And this is what we want to start with right here. So we know that the potential above the plane is going to be some superposition of the potential given from our rod of positive charge density lambda, but also including the image charge of negative charge density negative lambda. And this is because, again, in the other method of images problems that we have seen, when we are looking at the region above the conducting plane, we know that the potential is going to be the sum of the superposition of the charge that we have in our setup, the actual charge that's present, in combination with the image charge. And that's the beauty of the method of images, is that we, instead of having to find out what is the charge distribution on the conducting plane, we can just use the image charge and simplify things much quicker. So we'll have that potential above the conducting plane will be the sum of the two potentials, the one from the one with positive charge density lambda and the one with the negative charge density negative lambda, which will just be lambda over 2 pi epsilon naught ln of s prime plus negative lambda over 2 pi epsilon naught ln of s double prime. And here I've used two positions, s prime and s double prime, to indicate that when we're looking at a position above our connecting plane, we have the position of that point we're looking at of interest. It will be a distance s prime away from the positively charged rod, and it'll be a distance s double prime away from the negatively charged rod. So that means that s prime for us will be x squared plus y squared plus z minus d squared, square rooted. And that's the position away from our positively charged rod above the xy plane. And our s double prime will be x squared plus y squared plus z plus d squared, where the plus d, now we have a positive here because of the fact that we start below the connecting plane. Of course, in this question we were looking at the position 0, y, z, where x was equal to 0, so we can just get rid of that x squared right away. And substituting into the formula down here, I would pull out the common factors, and we have essentially the ln of y squared plus z minus d squared square rooted, and then that will be divided by y squared plus z plus d squared square rooted. Make sure you have a lot of brackets. Yeah. And I did a simplification here where I have that ln of s prime minus ln of s double prime is simply ln of s prime divided by s double prime. That's a property of logarithms. So we can do one last final step where we see that there's a square root, and again, from the properties of logarithms, we can pull that outside of the logarithm, and we have the final answer of ln of y squared plus z minus d squared over y squared plus z plus d squared. So, to summarize how I got to this final answer, we started with the diagram of our conducting plane with the positively charged infinite rod, a distance d above that conducting plane with a width w, and a charge density of positive lambda, and that was running in the x-axis. We wanted to find the potential at some point 0, y, and z above this conducting plane. So the x position was 0. We can do that by recalling right away what is the electric field of a line of charge and determining the potential of that line of charge from that electric field. So we just used Gauss's law quickly to find out what was the electric field, and then we found the potential was just lambda over 2 pi epsilon naught, the logarithm of s, where s is our position away from that positively charged rod. And by superposition, this is what the beauty of the method of images problems is that we can essentially find the potential above this conducting plane by summing the potential from this positively charged rod with the one from the negatively charged rod. So we say take v plus v minus. We simply solve that through, given what we know the potential of a single line of charges. In this case, we have two positions. We have s prime and s double prime, where the s prime is the position away from our positively charged rod, and s double prime is the position away from the negatively charged rod. Again, we set x is equal to 0 because we're looking at the point x equals 0 and yz. We can plug in the s prime and the s double prime into our equations, making the simplification from the logarithm rules. And we have this z minus d and z plus d difference in the fact that the positively charged rod initially starts above the conducting plane, and the negatively charged rod starts below. So again, it's back to that point charge above, point charge below method of images problem, where we take the superposition of the potentials of each one individually. And in that case too, we also had a z minus d and a z plus d. Then we simply have to do some algebra where we solve through, we plug in all the values. Again, we take the property of logarithms where we can pull the square root outside of the logarithm, and we end up with the potential of the configuration above the conducting plane at some position 0, y, and z is v is equal to lambda over 4 pi epsilon naught times the logarithm of y squared plus z minus d squared over y squared plus z plus d squared.